Okay? So up until now, our discussion of aldehydes and ketones have been all about the fact that that carbonyl carbon is a good electrophile, right? We talked about the reasons why it's a good electrophile, but we've seen all these reactions where we have some nucleophile attacking that electrophilic carbonyl carbon. We divided our world of nucleophiles up into acidic and basic nucleophiles. Our basic nucleophiles are easy to spy. They have those net negative charges. All right, there were a few exceptions. These special hydrogen nucleophiles are hydrides, as well as our Grignards, which don't have that net negative charge, but they're also those basic conditions. And then we have the neutral form of those nucleophiles, which are our acidic condition nucleophiles. But importantly, regardless of whether it was acidic or basic, that informed what our reaction mechanism should look like. But our reactions were the same, where we had this nucleophilic addition. We added our nucleophile to what was formerly that carbonyl carbon, and that carbonyl oxygen formed that alcohol group, right? And that was the same whether we were talking about acidic or basic conditions. So here's my basic nucleophile. I get my product where my nucleophile is added to that carbonyl carbon. Under acidic conditions, same nucleophile, rather it would be the neutral version. All right, gets added to that carbonyl carbon, and I'm retaining that carbonyl oxygen. All right, so we've had these nucleophilic addition reactions. One of the things that we noted that we were going to exclude from that list are these nitrogen nucleophiles here, right? These are indeed, this amide ion here is indeed a very good base, and it's a nitrogen nucleophile. But what we're going to see next chapter is that these really strong bases react with our aldehydes and ketones in a different way than these nucleophilic addition reactions. We can also note that this nitrogen nucleophile did not appear down here under acidic conditions either. Right? So we had our acidic condition nucleophiles. We did not see a nitrogen nucleophile where we just took this negative charge and protonated it like we were doing with our oxygen nucleophiles. All right? And that's because one of the things that we need to remember about our nitrogens, this example here, ammonia, this is a weak base as well as a good nucleophile, right? And by weak base, in the grand scheme of things, it's a pretty good weak base. Not super weak, right? But actually very readily plays the role of a base in many reactions. So if we did have any sort of acidic conditions, let's say that we had hydrochloric acid, all right, we wouldn't see our nitrogen playing the role of a nucleophile with an aldehyde and ketone. We would see it playing the role of a base, creating this ammonium ion, so just a classic acid-base reaction here. And importantly, that ammonium ion that we form under acidic conditions is not a nucleophile. So nitrogen cannot readily play the role of a nucleophile in the presence of a strong acid because it itself is a pretty good base. It'll just get protonated here, and this is no longer a nucleophile. How do I know it's not a nucleophile? It's got not only does it not have a negative charge, it's got a positive charge, and it doesn't have a lone pair. It can't donate any electrons at all, right? So this thing right here, as soon as we protonated nitrogen, we turn it into an absolute terrible nucleophile, something that cannot be a nucleophile. So under acidic conditions, all right, so we're just going to note here, amines are not nucleophiles under acidic conditions. They are instead going to be bases creating ammonium ions or aminium ions, and those are not nucleophiles. All right, so again, we left off nitrogen up here. We said that's because something weird's going to happen with our basic nitrogen nucleophiles. We also didn't include nitrogen down here, and that's because amines cannot be nucleophiles under acidic conditions. All right? That doesn't mean that we're not going to talk about nitrogen. It means that we're going to put them in their own special camp here. All right? So now we're going to start a discussion of our nitrogen nucleophiles. separate from all our other nucleophiles that we've been discussing. All right, so they get their own special little category here. We want to think about them differently than how we've been thinking about all our other nucleophiles in this chapter. All right, and the first big difference is going to be the conditions under which we have nitrogens reacting with aldehydes and ketones. We said it wasn't going to be basic conditions. It also can't be acidic conditions. These are going to be our nucleophiles that react with aldehydes and ketones under what we're going to call neutral conditions. All right, and remember, these conditions were all about putting guardrails under what type of intermediates we were allowed to see. Under basic conditions, we should only have negatively charged intermediates, whereas under acidic conditions, we should only have positively charged intermediates. All right, under neutral conditions, we're going to see both negative and positive intermediates. All right, we don't have those same charge restrictions that we did under acidic or basic conditions. All right, now I am lying to you a little bit. We're going to call it neutral conditions because it's going to be a helpful reminder as to what intermediates we're allowed to see, similar with what we were doing under acidic and basic conditions. All right, but truthfully, these nitrogen nucleophiles, it does need to be slightly acidic. All right, with a pH around 5. Nowhere near the low pH that we're talking about when we say acidic conditions. When we say acidic conditions, we're talking about like pH 0, something ridiculously acidic. We are now under slightly acidic conditions. Importantly, that means that we do have hydronium ions present. There is some small concentration of hydronium floating around in that solution, which is going to be important. We can't have it be too acidic, though, because of what we just discussed, right? We can't be forming any ammonium ions. So we need it to just be very slightly acidic, where we have a few hydroniums floating around, but we're allowed to see both negative and positively charged intermediates, unlike our true acidic conditions, right, where we're not allowed to see any negative intermediates. All right, so then what's going to happen here? Let's take an aldehyde or ketone. We're going to work with acetone as our sample molecule. All right, and actually before we get started here, we're going to be good, and I'm going to title this primary amines. All right, we're going to see slightly different reactivity between primary and secondary amines for our aldehydes and ketones. All right, so we're going to take this acetone here, this ketone, and we're going to react it with a primary amine. Primary amine meaning that nitrogen is just bonded to one carbon, so there are necessarily two hydrogens on a primary amine. All right, and if I'm going to tell you that this first step involves these two molecules here, I want everybody to take a second and identify what your nucleophile is going to be and what your electrophile is going to be. What's your nucleophilic site and what's your electrophilic site? All right, what's our electrophilic site here? That carbonyl carbon. Holy hell, if there isn't anything that you took away from last week, it should be that electrophilic carbonyl carbon. Right? Over and over again, that carbonyl carbon playing the role of the electrophile. So then if this amine is my nucleophile, what's my nucleophilic site? Right? What is the title of our friggin' section here? Nitrogen nucleophiles, right? So we're talking about nucleophilic nitrogens. And what do nucleophiles do to electrophiles? Attack. All right, so now following our electron pushing arrows, everybody take a second and draw our intermediate. right, so now we have that oxygen single bonded. We also have that new carbon-nitrogen bond. All right, what should be the charge on my oxygen after it accepts that pair of electrons? Negative. All right, and my nitrogen now, it's got these 2 protons and this 2 carbon chain here, plus that extra bond, so for a total of 4 bonds. So what's the charge on my nitrogen? Positive. And look at how now we have broken our rules for acidic and basic conditions, which is why we classified this as a special neutral conditions reaction. We see both a negative charge and a positive charge all in the same intermediate here, something that wouldn't have been allowed under acidic or basic conditions, right? So again, nitrogen nucleophiles are weird because we have a different set of conditions than all of our other nucleophiles, where we're going to see both negative and positive charges in our intermediates. All right, now everybody's going to take a second and put in the electron pushing arrows in order to create our intermediate here, where we have that neutral nitrogen, that neutral oxygen, that alcohol group. All right, what we call a carbonyl amine. All right, everybody take a second and put in the electron pushing arrows over here to get to our carbonyl amine. All right, we need to make a new oxygen-hydrogen bond. I need to break an existing hydrogen-nitrogen bond. So we're going to have our oxygen lone pair reach out, grab that proton, take that pair of electrons to that nitrogen. All right, you'll see in some textbooks this broken up into 2 steps where there's a proton donor and a proton acceptor. I don't know, we can just do it all in one step, this intramolecular rearrangement here. We have this basic oxygen and this acidic nitrogen. That basic oxygen is going to grab that proton, giving that pair of electrons to that nitrogen. And this forms our carbonyl amine, all right? Carbonyl amine, because it's got an alcohol group and an amine group all in the same molecule. And this is our regular nucleophilic addition product here. Just like we saw over here where we added our nucleophile to that carbonyl carbon, retaining that carbonyl oxygen as an alcohol group, that's exactly what we get here. Okay? The weird thing is that we have these neutral conditions where our intermediate here has both negative and positive charges. All right? So again, nitrogen nucleophiles we put into a separate category because of these conditions here. Did you have a question?
Yeah, if I have it, I use the hydronium ion to protonate the oxygen and then the H2O.
That's fine.
All right,
Yeah, that's cool. Yeah, you could break it up into those 2 steps, right? This is just one way to do it in one shot here. Yeah. Okay, so weird nitrogen nucleophiles because we have these neutral conditions. The other weird thing is that we don't stop here. All right, this carbonyl amine is not what we isolate as the product of this reaction. This thing's going to keep on going and form a different product here. So this is what we would expect given everything else that we've discussed, but now we're going to keep going here. Okay, like I said, that we have to have those slightly acidic conditions. Hydronium is going to be an important part of this reaction. And this is where it gets its moment. We're going to protonate that alcohol group. All right, so we don't stop at our carbonyl amine. Instead, we've protonated that alcohol group. So this intermediate here, we see this positively charged oxygen here with these 2 hydrogens. We've seen this group a lot. What does it play the role of in our reactions? Leaving group, all right? And so that's exactly what's going to happen here. Now, importantly, it doesn't just leave all on its own, right? We don't just kick that off and form this carbocation. We had this discussion when we were talking about our acetyl formation, kind of that weird reaction between alcohols, all right? We had a similar intermediate here, but we said we don't just kick off that water and form that incomplete octet carbocation. Instead, that pair of electrons on that oxygen comes down, and that's what kicks off that water, right? That's a way to do it to not form a carbocation so that everybody has a complete octet. And we're going to see the same thing here with our nitrogen. We need to kick off that good leaving group. Those are good instincts, right? We're definitely trying to get rid of that. But we don't just kick it off and form a carbocation. It's the pair of electrons on that nitrogen that comes down and kicks off that water leaving group. So everybody's going to take a second and draw me my intermediate here, following our electron pushing arrows. All right, so now I have this carbon-nitrogen double bond, all right, because that pair of electrons was used to form a new bond here, that nitrogen has a positive charge. So we got one more step to go here to create our neutral product, and that is going to be to deprotonate our nitrogen, all right. In terms of what's in our reaction mixture, we have our amine, which is a good base. So there's an argument to be made for the amine playing the role of the base here. But also because of our concentration of our weak acid, our dilute acid, there's also going to be a bunch of water molecules present. And so you got a good argument based on concentration that there's more water floating around. Either one of these you can use as your base in this step. I'm not going to be too picky about that. Again, there's kind of a good argument for both of them. So we need a base to come and deprotonate our nitrogen, giving us our final product. All right, and this final product here is weird. We got this carbon-nitrogen double bond in our final product. All right, we call this thing not an amine with an A, but an imine with an I. Okay, so nitrogen nucleophiles, weird in two ways. Number one, because of those neutral conditions, right? Because we're going to see intermediates with both positive and negative charges, like we did in that very first step. The other way that nitrogen nucleophiles are weird is we don't just get that regular addition product that we've been seeing over and over again. This will continue to react where notice that we've completely lost that carbonyl oxygen in this process, right? We end up, that nitrogen ends up kicking off that carbonyl oxygen all together in this reaction, replacing it to form this imine product. All right, so again, nitrogen nucleophiles, we're kind of taking and talking about in a separate category because they behave a little bit weird. And we distinguish between primary amines and now our secondary amines. We're going to see something very similar but slightly different here. All right, so first of all, by secondary amines, I mean that nitrogen is not bonded to one, but to two carbons, meaning it's only got one hydrogen attached. All right, and given what we've discussed for primary amines, I want everybody to take a second and give me my mechanism all the way to that carbonyl amine intermediate. All right, that regular nucleophilic addition product that we would expect, given everything we've discussed. All right, we have our nucleophilic attack forming that neutral intermediate with a positive and a negative charge. We need to protonate our oxygen and deprotonate our nitrogen. All right, we can do that all in one shot here. Forming that carbonyl amine intermediate. All right, just like with primary amines though, we don't stop here. All right, so everybody take a second and I want you to complete those analogous 2 steps just like we saw before. All right, we're gonna do a proton transfer step to our alcohol from hydronium. And then we're going to kick off that leaving group. And again, the impetus to kick off that leaving group comes from that lone pair on that nitrogen. All right, again, leaving us with that carbon-nitrogen double bond. Okay, and this is where we're going to see a deviation in our reactions between primary and secondary amines. Up until this point, everything's been the exact same, right? Nucleophilic attack, then we had that intramolecular proton transfer, then we got rid of that alcohol group by protonating it and kicking it off with that pair of electrons from our nitrogen. But unlike our primary amines, when we got here with our primary amines, we had this hydrogen that we could get rid of to create our neutral product. Here, with secondary amines, we don't have any hydrogens to get rid of, right? We still need to make sure we get this neutral product, but how are we going to do it since we don't have any nitrogens to remove, any hydrogens to remove? Importantly, we don't have any hydrogens to remove on this nitrogen here. What we are going to see is the hydrogen on a neighboring carbon playing an important role in this reaction, all right? So what we're going to do is just kind of make a note here, since this is something that's a little weird, something that we haven't seen before. All right. our hydrogen on a neighboring carbon is going to be removed. All right, and again, if you used that stronger of the two bases, the amine, to do it, that would be fine. Or if you used that higher concentration of weak base water molecule to do it, that would be fine. Either one of those I would accept, but we need a proton, a base, something to remove this proton here. Okay, now we're not quite done yet. The whole point is we need to make this nitrogen neutral, so it's going to accept that pair of electrons. But we can't just stop here because all of a sudden we're violating our octet rules. So what's going to happen is that hydrogen's going to be removed, and that pair of electrons from that carbon-hydrogen bond is going to come down to form a new carbon-carbon bond. So everybody take a second following our electron pushing arrows. Give me my product of this reaction here. Okay, so importantly, we don't have a carbon-nitrogen double bond. We're going to see a carbon-carbon double bond between that neighboring carbon, and the one bonded to that nitrogen. Okay. So whereas our primary amines formed imine products, our secondary amines form what are called enamine products. Ene because we have that carbon-carbon double bond, amine because there's an amine group. Yeah. We're actually going to find they're super useful. We're going to find in our next chapter as well. But yes, these are isolatable. I will say one more thing that we're going to do to our reaction mechanisms to make them super truthful here is we're going to note that this is a completely reversible reaction. So if instead I started with this enamine and put that under acidic conditions with our oxygen nucleophiles with water, I would instead form a ketone here. So each one of these steps we're going to make sure to note is reversible here. Okay, same with our primaries. If we're being good here, we should use these double-headed arrows to show that these are reversible steps here. But yes, you can isolate enamines. All right, so nitrogen nucleophiles. We're talking about them separate from all of our other nucleophiles because we're going to note these two important differences. Number one, they react under neutral conditions, meaning we're going to see both positive and negatively charged intermediates. But also, we don't get our normal old nucleophilic addition product. It keeps on reacting in order to form these weird, depending on whether we're talking about primary or secondary amines, imine or enamine products. All right, so just to take a second and to summarize those nitrogen nucleophiles. All right, let's get we were working with acetone, we'll pick a different one here. Let's do cyclohexanone. And just so we can have this all summarized, we're going to do one reaction with a primary amine. And then put that right next to a reaction with a secondary amine. Everybody take a second and give me my product of these reactions. All right, so with primary amines, we get that imine product, and with secondary amines, we get that enamine product. Cool. And we will actually see these enamines come up again. They turn out to be very useful in a type of reaction that we'll cover in the next chapter. All right, so then we talked about these nucleophilic reactions, right, where our aldehyde or ketone is playing the role of an electrophile, reacting it with a variety of different nucleophiles. All right, we got a few more reactions of aldehydes and ketones to discuss, and we're going to lump this into this other reactions category. All right, the previous ones, they all had this kind of common theme that we were following for each one of these reactions. These ones are going to kind of be like one-off, sit by themselves kind of reactions, things that we just got to know here. All right, the first is what's called a Wolff-Kishner reaction. Kishner. Okay, and first we're going to take our aldehyde and ketone and we're going to react it with this very special primary amine here, what's called hydrazine. All right, hydrazine are these two NH groups single bonded to one another, NH2 groups. All right, if I'm reacting my aldehyde or ketone with a primary amine, what's my product going to be? That imine. All right, this imine's a little special because it's got that nitrogen-nitrogen bond. All right, but a Wolff-Kishner reaction isn't where we stop there. We're going to take this and follow it up with some hydroxide source like potassium hydroxide. All right, and what that's going to do is remove protons from this hydrogen, creating these nitrogen-nitrogen bonds. And eventually that nitrogen is going to fly off as nitrogen gas, leaving us with this fully reduced carbonyl carbon here. So I've replaced that carbonyl group, that carbon-oxygen double bond, with these two carbon-hydrogen single bonds. So I've turned my ketone into what functional group? An alkane. All right, I've just fully reduced that carbonyl carbon, got rid of all those carbon-oxygen bonds, and replaced them with carbon-hydrogen bonds. Okay, so Wolff-Kishner here, we're going to fully reduce our carbonyl to an alkane. All right, effectively, our Wolff-Kishner reaction just chops off, chops off that carbonyl group. right? Breaks that carbon-oxygen double bond, replacing it with 2 carbon-hydrogen bonds. All right, our next reaction in this other category is what's called a Wittig reaction. All right. This Wittig reaction here uses this very weird reagent here, this Wittig reagent called an ylide. All right, so pH3P, what does that mean? That means we have a phosphorus that's got 3 bonds. Does anybody know what the pH is? pH is a phenyl group, which is another way of saying a benzene ring. So we have this phosphorus atom bonded to these 3 big old benzene rings. Which is pretty interesting, but importantly, that's not what's going to be involved in the reaction. It's this double bonded alkyl group here. All right, this is what's going to be important for our reaction. This is the important part of our reagent here. All right, that R group just standing for some alkyl group that is double bonded to that phosphorus in our ylide. All right, so if we take a aldehyde or ketone, we react it with this Wittig reagent here. I'm going to leave it abbreviated as pH3P. But then I'm going to show a specific alkyl group here. All right, we'll put 3 carbons on there. All right, in these Wittig reactions, we're going to replace that carbon-oxygen double bond with a carbon-carbon double bond. Forming an alkene product, all right, where we've added these, in this case, 1, 2, 3 carbons from our Wittig reagent, from our ylide, onto our aldehyde and ketone. All right, so we've replaced that carbon-oxygen double bond with a carbon-carbon double bond. All right, so our Wittig, let's just make note, we replace that carbon-oxygen double bond with a carbon-carbon double bond. All right, and the last two in our weird reaction category here, our other reaction category, are these cyanohydrin reactions. All right, so what the heck is a cyanohydrin? This we've actually already seen before. We looked at one of these last time with our carbon nucleophiles. We talked about one of our good carbon nucleophiles were those cyanide ions. So if I took my ketone here in the presence of sodium cyanide and hydrogen cyanide, everybody take a second and give me my nucleophilic addition product. All right, so we get that nucleophilic addition product. We've added on that cyano group. This thing right here is what's called a cyanohydrin. And so far, nothing special here. All right, just like we learned how to make these things before, putting in our basic nucleophile, we have that basic nucleophile attached to that formally carbonyl carbon, and that formally carbonyl oxygen is now that hydroxyl group. All right, the new thing is what we're going to do to these cyanohydrins. All right, so there's two follow-up reactions that we can do here. One is to take that cyanohydrin and put it in the presence of a dilute acid and heat. All right. Importantly, when we do our addition reaction, we've added this extra carbon here, right? That carbon that was part of that cyanide ion. If we take this thing in the presence of acid and heat, what we're going to do is oxidize that carbon to a carboxylic acid. All right, so we have this carboxylic acid group located one carbon away from that alcohol group. That's what we get if we take a cyanohydrin and treat it with dilute acid and heat. All right, and the last one in our other category here is if we, instead of oxidizing that carbon, we reduce it with our lithium aluminum hydride and acidic workup. That will reduce that carbon, that cyano group. All right, we will get, instead of a carbon-nitrogen triple bond, a carbon-nitrogen single bond, which means that we have an amine group. All right, I kind of feel like this is an odd place to put these reactions, but whatever, they tacked them on to the end of this chapter here. We learned about how we can create these cyanohydrins by treating our aldehyde and ketone with that basic nucleophile, that cyanide ion. And now we're talking about things we can do with our cyanohydrins, either following up with dilute acid and heat to create a carboxylic acid group, or reducing them with lithium aluminum hydride to create that carbon-nitrogen single bond and our amine. All right, so we got these four reactions under this other reaction category. Our Wolff-Kishner reaction, where we can chop off that carbonyl oxygen, fully reduce that carbon to an alkane. Our Wittig reaction, where we replace that carbon-oxygen double bond with a carbon-carbon double bond. And then lastly, these two cyanohydrin reactions, where we form our nucleophilic addition product, our cyanohydrin. And then we have these two follow-up reactions to either oxidize or reduce that functional group. Cool. All right, that's all I got for you.